Good evening. I welcome you all for the week two lecture on Geotechnical Engineering Laboratory. Myself, Sandhya here. Okay, let's move on to the today's week discussion. In last week class, one of them have asked for the hydrometer calculation. So, I'll discuss brief about hydrometer calibration and calculation. Okay. So, first of all, as you remember from last week class, hydrometer is used for grain size distribution analysis of fine grained soil. When you are going to have fines passing through 75 micron sieve, if it is going to be more than 12 percentage, then we have to conduct hydrometer analysis. So why is that 12 percentage? Means it is a limit given used for classifying the soil. Okay, where you will have your influence of the fines in the behavior of the soil. So if it is going to be less than 12 percentage, there is no need to do hydrometer analysis. But if the percentage fines passing through 75 micron sieve, if it is going to be more than 12 percentage, then we will be doing hydrometer analysis. So for hydrometer, from our raw soil which is soaked in water for 24 hours, it will be washed in a 75 micron sieve, and you will have fines passing through the sieve, and it will get collected in a bucket that is placed below, and the top you will have coarser fraction which is retained. So this finer fraction which is collected below along with water, it will be allowed to settle for 24 hours. And then what we will do is we will remove the top water slowly. Then we will have the fines at the bottom settled well. It will be kept in oven. So once it is kept in oven, and after the next day it will be taken out, and you will have kind of fine chips. If you observe for expansive soil, it will be something looking like a chocolate chips. So very thick crust of chocolate kind of pieces we will be getting. So these are the fines. So we have to take 50 grams of that. We cannot use the entire soil, so you have to take 50 grams of the oven dried 75 micron sieve passed soil, and we have to add sodium hexametaphosphate and sodium carbonate to that soil, and we have to soak it in water. So there are prescribed levels like zero point 0.7 grams and 3.3 grams of the chemicals should be added, and it will be again soaked in water. Then it will be then again after 24 hours it has to be mixed well in a stirrer, and transferred to a 1000 ml jar. Okay, so this is how we make the sample for our hydrometer. So once we do the hydrometer, we have to first start the calibration. So you can see this is your hydrometer. Okay, this is your hydrometer. We have a stem and a bulb, and this is our 1000 ml jar. Okay, so we have made the solution for 1000 ml, and then we have to we'll be doing our test, placing it, the hydrometer inside. So before that we have to make a chart. Okay, that we call it as a calibration chart. So first we have to measure what is the volume of this hydrometer. We have to find out what is the volume of this hydrometer. So how do we find out? We have two methods, two ways. One is we fill a jar, a similar 1000 ml beaker with 800 ml of water, just distilled water. We fill it, and we insert this uh, hydrometer inside that beaker of 1000 ml water. Okay, so we'll know how much level it is increasing in the, because by insertion of hydrometer, you know that the volume of water will increase. So noting down that volume, for example, if it is increased to 950, so the difference is going to be 150. So that will tell you that volume of the hydrometer. Okay, so this difference will give you the volume of the hydrometer. Or else what other method we can do is we can measure the weight of this hydrometer. What is the weight? So the weight is directly equated to its volume. So that way we can find out the volume of the bulb. Okay, so we are finding this stem, it is negligible, so we are ignoring that. Okay, so we are not minusing or anything. So either we can insert it in a 1800 ml water filled beaker and find out how much level of water is increasing. That difference will give you the hydrometer volume, or we can simply find the weight of the hydrometer. So now we have found out what is the volume of the bulb. Next thing is, we have to find out the area of cross section of the beaker that we are using for the test. Okay, so we know that it is a 1000 ml beaker. So how do we find the area of cross section? We have to measure how much centimeter is between two graduations, how much length, how much distance or how much length is there between two graduations, and we have to get the area by dividing it by finding the volume between that to graduation. For example, see, this is going to be 100 cc of water. So 100 cc of water divided by 5 centimeter, that is a length. I'm just putting as an example. So 5 centimeters is the length between these two graduations, and the volume of water in this between two graduations is going to be 100 ml. So that will give you the area of cross section of the beaker. Okay, so volume is area into length. Volume is area into length. We know the volume, we know the distance, so we can find the area. That is the thing. Okay, so we have now found out the area of cross section of this beaker. So what we have to do is, from the neck to the bottom we have to measure what is the length. So this is the neck of the hydrometer, and from here till the bottom we have to measure what is the height. So that will give you the height of the bulb. And we have to measure what is the distance of the first graduation. That is, this is the first graduation from the center of the cylinder, from the center of this bulb, that we have to note down. Okay, so first we have what we have to find out. We have to find out the volume of this hydrometer. Then we have to find out the area of the beaker. Then we have to find out what is the height from the neck to the bottom of the bulb. Okay, so that height we have to note down. And from the distance of the nearest calibration from the neck, that also we have to note down. Okay, so as I said, you can see here. So this is the neck of this. So from here the nearest graduation, like sorry, from the center, from the nearest graduation, that measure height also we have to note down. So I'll show you an excel sheet where I have calculated. So what we are going to do is, we are going to create a chart like this, that is effective depth versus your hydrometer reading. This is the chart that we require. That is what we call it as calibration chart. So we are going to create this chart. So how do we get this chart? So these are your hydrometer reading. Okay, and this is the distance of the hydrometer reading from the neck of the bulb. Okay, so each reading, you can see we have measured d1 d2. So these are the graduations from the neck. From this is the neck, from the neck what is their distance. So we have to actually trace the hydrometer in a paper. That also we have to do. We have to trace the hydrometer in a paper and we have to mark it. In that manner also we can do. Okay, so if we know what is the first distance, this d1, we can add plus 2 centimeter. The distance between one graduation to another graduation is 2 centimeter. So if I know this distance, if I add plus 2 with that, I can get all the distances. Not necessary that I have to measure each and every graduation. Okay, so these are the hydrometer readings. So this is the first reading. Here they have taken a different value. It depends on the measurement way and things. Okay, uh, so you will be measuring what is the corresponding height from the neck of each reading. Then you have to substitute in this formula, that is h plus half h minus vh by a. If you see the video of the week, this formula is derived. It is called as immersion correction. Okay, because of immersing the hydrometer, there will be increase in volume and etc. So this formula is derived as a immersion correction factor. So this will help you to get the effective depth. So we have to substitute this h value, small h, vh and a. So we know what is vh. Vh is going to be the volume of your hydrometer, and your a is going to be the area of the measuring cylinder. Okay, and your small h is the this distance, your height of the bulb, this height. Okay, in this height of the bulb, that is going to be a small h, and this capital H is what we are measuring the distance of each graduation. So when we substitute this, we'll be able to get this effective depth. I'll just go to the Excel sheet. Yeah, you can see here. So what I have done is, this is the hydrometer reading. So I have measured for the first reading and I have added plus 2. If you see here, I have added plus 2 with each of the above reading. Okay, so I have found out h plus h by 2, and then I have found out h plus h by 2 minus vh by 2a. The same formula, but in the form of Excel sheet. Okay, so once I know what is the hydrometer reading and this effective depth, this graph is plotted here. So here for research purpose, we generally go for two graphs. One is going to be called as that is till 4 minutes of time interval. We'll be using one equation, and another 4 minutes we'll be going for the another equation. For your, I mean, for just field purpose or field purpose, I can say that you can go for one graph itself. Okay, so I have plotted this graph. Once again, okay. So what I have done, I have got the hydrometer reading and I have measured it from I have this h by 2. H by 2 is this value. H plus h by 2, that is your 8.4 plus zero point 0.8 I have measured, and I have added plus 2 with all the values, and I have found out this h plus h by 2 minus vh by 2a. Okay, so this graph, if you observe, it is between uh, hydrometer reading and this value. This line is what you have to know. I'll just delete this. Okay, you no need to confuse lot. Okay, so this graph between hydrometer and this equation will be plotting. So this we call it as a calibration graph. Okay, I have put a equation on that. Why? Because is so that it will be easy for us to do further calculation. Okay, fine. So you have to get this calibration chart before the start of your experiment. Fine. So now we have our calibration chart with us, which is plotted between your effective depth and hydrometer reading. Okay, fine. So next, what we will be doing is, so for different time, once you have to shake the you have to shake the solution, that's the soil that is having the sorry, the beaker with the soil solution. Okay, you have to shake it well vigorously, you have to shake it, and once you place it, you have to drop the hydrometer inside slowly and steadily. So you have to start the timer once you drop the hydrometer inside the suspension, soil suspension. So for different time interval, okay, for different time interval, you have to note down what is the hydrometer reading. So the hydrometer reading will be displayed. The hydrometer reading is the one which is be coinciding with the top surface of the solution. Okay, so you'll be noting down what is the hydrometer reading. We cannot leave the hydrometer for the entire time inside the suspension. After some time, like for after some 8 minutes or 15 minutes, we have to take the hydrometer and put it in the clean water, because if you are going to do that, then it is like the soil suspension gets deposited at the center of the bulb. Okay, so after some 15 minutes, you have to take the hydrometer from the soil suspension and put it in the clean water. And once that particular time comes, like for when you are coming closer to 30 minutes, for at the 29th minute, you can take and drop it again into the soil suspension. Okay, so you will be noting down at different time what is the hydrometer reading, then what is the temperature. So you have three corrections. One is temperature correction, dispersive correction, and meniscus correction. Okay, so temperature correction, there is an equation you can get at the particular temperature what is the what is the correction value you can get from the equation. And dispersive correction and meniscus correction, for dispersive correction you have to drop the hydrometer in a beaker containing water and that chemicals. We added two chemicals if you remember. So you add the same weight chemicals, same amount of chemicals to the water, mix it well, I mean dissolve it well, then make it to 1,000 ml and you have to drop the hydrometer. So the hydrometer may show some value, so that is going to be your dispersive correction. And meniscus correction, you have to place the hydrometer in distilled water and it may show some reading, so that is going to be your meniscus correction. Okay, so you'll do corrected reading. So corrected reading is observed reading minus meniscus correction. So we'll apply the other two corrections finally. So you have a corrected reading here. So effective depth, for this corrected reading you have to find out, for this corrected reading from the graph, where is the effective depth. That is what we want. For example, for 31 we have to find out where could be the what could be the depth from this chart. Okay, so instead of going and searching every time, I have used this equation. This is the equation of this line. So 0.4x plus 19.76. So if you see here, this x is nothing but your corrected reading, where your corrected reading is for the reading which is done after meniscus correction alone. Okay, so minus zero point 0.4 into this corrected reading plus 19.76, that is going to be your uh, equation. Okay, so you will get a line like this. So there's the equation here. So from this, that is a reading, that is a corrected reading. Okay, like this you will be getting all the values. Then you have to find out what is the particle diameter. So your particle diameter equation here, if you see here, the particle diameter is, this is the equation. When we just rearrange the variables, you'll get a equation around like this: square root of 30 mu by 980 into g minus g1 square root of he by t. I'm just rearranging this mu is nothing but the viscosity of water. Okay, so from this formula you can find out what is the diameter. So I have substituted the formula here. Okay, I have created the formula here. So your h is nothing but this effective depth divided by time. Okay, time factor. So I have substituted the particle diameter which is from obtained from this formula, and then I'll be finding what is the percentage finer. So for finding percentage finer, you have to apply the corrections, other corrections like temperature correction and dispersive correction to this value, and then you have to find out what is the percentage finer. Okay, so you will get the, ultimately you will be getting particle diameter versus percentage finer. Okay, so you have to plot the graph between percentage finer and particle diameter. So this percentage finer is for 50 percentage, 50 grams of soil. You have taken only 50 grams of soil. So for that we are calculating this percentage finer. We have to know for exact amount of fines that is collected. For example, the fines collected was around 400 grams. So for 400 grams, what could be this percentage? That is what we put it in a combined graph like this. I have put as you can see here, this 94 into, for example in my case it is going to be like 458 grams of fines around, for from which is taken from 500 grams of raw soil. So you'll be multiplying with that ratio and you'll get a final value. Then you'll be plotting your hydrometer graph like this. So once you plot this graph which is particle diameter versus percentage fines, you have to see for what is the percentage of clay that would be present. So your percentage of clay is nothing but which is going to be lesser than 0.002 size. Okay, so 0.002 size, so lesser than 0.002 is going to be around 68 percentage. So you have 68 percentage of clay here in your soil. So this is how we get the percentage of clay. for silt it is going to be between 0.002 to 75 micron. So we can draw a line here and find the difference in percentage. So for example, this is going to be 90 minus 70 roughly, so it is going to be 20 percentage of silt. Okay, so we get the percentage of clay and percentage of silt from this graph. Okay, so we use directly from excel sheet, we can get what is the values, I mean what is the required percentage of clay and silt. Okay, so this is all with your hydrometer. Okay, so we'll go to the week 2 lecture on Hatterberg limits. So when you're going to have fine grained soil in your site, okay, we have to classify the soil. For classifying a fine grained soil, we will be using Atterberg limits. If you remember your grain size distribution, where we classify a gravel or a sand, the grain size distribution chart for classifying the gravel or sand, it will be the value of cu and cc is enough. From that we can classify, well, if it is a well graded gravel or a poorly graded gravel, well graded sand, poorly graded sand, that way we can classify the coarse grain soil using the grain size distribution curve. But whereas when we want to classify the fine grained soil, we have to find out the Atterberg limits. Atterberg limits are nothing but water contents. So as I said, the behavior of clay is entirely dependent on its water content. So in 1911, the Swedish scientist Atterberg, he reported an extensive study on plasticity of soil. So he found out that with varying the water content in the soil, its consistency is varied. So he found out the liquid limit and plastic limit, which are nothing but water content, which will help in classifying the behavior or classifying the soil. So you remember this graph always, the graph between volume and water content. Okay, so this is the graph between volume and water content. So you have a straight horizontal line, and then there is a linear increase in the volume. Okay, so as when the soil is in with a very high water content and in a state of flowing consistency approximately, we call that the soil is in liquid state. Okay, and when the water content decreases slowly, so you can see that as I decrease the water content, the soil will transform from liquid to plastic state, where you can roll the soil. Okay, you can roll it into a ball kind of thing without forming any cracks. Okay, so that we call it as plastic state. And when you slowly decrease the water content still, okay, it will move to the semi solid state. And from semi solid state, when you still decrease the water, it will move to the solid state. Okay, so there are three water contents. One is going to be liquid limit water content, plastic limit water content, and shrinkage limit water content. So the basic of finding this is mainly to classify the soil, and also you can get an idea about the strength of the soil and its state of existence in the site, everything. Okay, so as far as fine grained soil is concerned, Atterberg limits are very much important to find out. So if you see this graph, so you can see that after shrinkage limit water content, even though when you decrease the water, there are still this much water is there. Okay, so even though if you decrease the water, there is no change in the volume. That is what very important to observe. Okay, so from liquid limit to solid, from liquid limit to shrinkage limit, when you decrease the water content, the volume is also slowly decreasing. The volume of soil slowly decreasing. But whereas when it reaches the shrinkage limit water content, even though if further you decrease the water, still this much water is there. Even though further if you decrease the water, there will be no change in the volume. The volume will remain constant. Okay, if you remember this, then it will be easy to remember the definition. So your liquid limit is a boundary between your liquid and plastic state, where it is going to have a very negligible shear strength. Shear strength is a very important factor in soil mechanics, where all your foundation and everything is resisted by the soil because of its shear strength. Okay, shear strength is something, a resistance against um, moving of particles over one another. That way I can easily tell you. Okay, so shear strength is something like where when you keep your foundation or a building over your soil, if your soil just moves away in lateral direction, what happens, the building will move down. Okay, it will sink, it will settle, it will tilt, so it will cause a failure. But whereas when it is going to have a very good shear strength, the soil will not move in lateral direction, so it will resist the load. Okay, so higher the shear strength, better is the performance of the soil. So when you are going to have it in liquid state approximately, so it will have a negligible shear strength. So plastic limit, so plastic limit is a water content at which where you can roll the soil. It is like a indication that the plastic limit water content is present in the soil, where you roll the soil to 3 thread and it will just start to crumble or crack. Okay, so that is a indication of your plastic limit water content. And shrinkage limit water content, so it is a maximum water content where any further reduction will not cause a decrease in volume of soil. Okay, so in all these water contents, it is said that the soil is 100% saturated in liquid limit, plastic limit, and shrinkage limit. So you can see that your shrinkage limit water content is a maximum water content at which even any further reduction in water content will not cause a reduction in the volume change. Okay, fine. So this is your liquid limit device. We call that Casa Grande liquid limit device. Okay, so and this is going to be your plastic limit. Okay, so where you roll the thread in the for 3 diameter and it will start to crumble. Okay, fine. So the other, there are some indices like parameters derived from these values, which will help in further understanding the soil. So plastic limit, plasticity index, plasticity index is a difference between your liquid limit and plastic limit. This is very very important. So when we classify the soil, we from our plasticity chart, so there is a plasticity chart. Okay, so for using this chart, we'll classify the soil. We'll classify the clay as low compressible, medium compressible, and highly compressible. Okay, so this is a ASTM chart. If you go for IS chart, there is one more classification. As I said, CI, clay of intermediate plasticity. So yeah, this chart is between plasticity index and liquid limit. So if we need to find out, we need to know what is the plasticity index in order to classify the soil. So as I said, plasticity index is the difference between your liquid limit and plastic limit. And then there is another index called as liquidity index. So liquidity index is a ratio between your NMC minus your natural moisture content minus liquid limit divided by the plasticity index. So this will give you the state of existence of the soil in the field, whether in the field the soil is in liquid state or plastic state or semi-solid state. Using there's a table, from that value, standard value, you can know that whether the soil is in soft condition, very soft or stiff condition, etc. And there is one more index called as flow index, which is going to be the slope of your liquid limit test. So in liquid limit test, we'll get a graph. So if you find the slope of that graph, that we call it as flow index. I'll come to that later. So okay, liquid limit test. So for liquid limit test, what are the apparatus required? Let's not see how many are there. Okay, fine. So for a liquid limit test, you have a Casa Grande liquid limit device. We have a grooving tool. So there are two grooving tools depending upon the plasticity or clay content. We may change to one to another. Then we have the soil of around 250 grams. Then we have the moisture cans, that is for determining the water content, and we have a spatula. So what we have to do is we have to mix the soil. Generally for research purpose, I think we will be following wet to dry method, we call that is wet to dry method. Means we will mix the soil with excess amount of water, and without any lumps or without any clots, we'll mix the soil uniformly. So you'll mix the soil uniformly and with excess amount of water, and like it is like in a little bit flowing condition. Okay, so and then we keep it in ziploc covers for saturation. So or equilibration we can tell. Okay, so after 24 hours we take that ziploc covers and we take the soil, transfer the soil to the glass plate and we will dry it. We'll dry the soil on a glass plate. So it will be slowly drying. We'll be mixing it uniformly, intermediately, so that it will have uniform distribution of moisture. So then we have to place the soil on the cup. Okay, so like we have to three-fourth of the cup has to be filled with the soil to the restricted height. It should not be overfilled or underfilled. Okay, so it has to be filled and you have to make a groove. So at center like this we have to make a groove. So once you make the groove, you have to start rotating the cup. So the cup has to be rotated at 2 revolutions per second, in the rate of 2 revolutions per second. So this groove will be closed at least for some 1 centimeter. Okay, so you have to see that it was closed. Then not necessary that entire groove has to be closed. So then we'll take the soil from both the halves. You know what is the empty weight of the container? Put the soil inside that, measure the wet weight, keep it in an oven, measure the dry weight the next day, then you get the water content. You have to note down what is the number of blows. Okay, so yeah, generally we start from 10 blows. So once the soil comes to 10 blows, you have to will be starting the test. If we are getting some 2 or 3 blows, we have to ignore that. Okay, so once we get 10 blows, then we take the soil again, we spread it. Then again we have to wait for some more time, dry it for some time, and we have to repeat the procedure. So this is what we call it as wet to dry method. There is another method called as dry to wet method, where you immediately add water to the where you add water in a slow manner. That is, you add little by little, you increase the water. Okay, initially you add very less amount of water, so you'll get a blows around 40 or 50. Then you remove the soil, then you add some more water, then you get around blows around 20 to 30 something. So here you are going in this from dry to wet method, you are slowly increasing the water. In wet to dry method, we are drying the soil, we are adding excess water and we slowly drying the soil, and we are finding out the same water content. Okay, so the advantage of using wet to dry method is, here it is ensure that the soil is homogeneously distributed with the water content, and also the soil is will be fully saturated. Okay, fine. So you slowly increase the water and make the paste, and you can repeat this procedure. Okay, so before starting the test you have to check for the height of fall and everything. Okay, so you have to make sure that the height of fall is going to be 1 centimeter of the cup. So you fill the cup, make the groove and close it. So you note down what is the number of blows, and you note down what is the wet weight plus tare, dry weight plus tare, empty weight of the tare, and measure the water content. And then you plot a graph between your water content and number of blows. So in a semi-log graph, if you remember, we use semi-log graph for grain size distribution also. So in a semi-log graph, you plot your points and you get a neat straight line. So from that you have to note down for 25 blows what is the water content. You have to find out this value. So this is the liquid limit. Okay, so liquid limit is the water content at which the groove that you are making will close for at 25 blows. Okay, so 25 blows you have to take it, strike at the line and find out what is the water content. So I said there is a value called as flow index. Flow index is nothing but the slope of this line. So you need to find the slope of this line. If your slope of this line, if it is going to be very much small, then it means that sorry, if it is going to be very much large, it means that the shear strength of the soil could be very less. Okay, so it gives you some idea without doing any complex test like triaxial or anything. So you can find out what is the shear strength of the soil. So the shear strength of the soil could be very less if the slope of this graph is going to be very high. Excuse me. Okay, fine. So we have found out what is the liquid limit. Okay, so liquid limit, at liquid limit, the soil will have a very less shear strength. Next is going to be the plastic lemon. So the same soil will be drying for some more time. Once our liquid limit test is over, we can use the same soil. So we have to dry it for some more time. We have to take some around 8 grams of soil and make it as a ball. Okay, so make it as a ball when you between your palms. You have to see, and you have to roll it on a plate. So if the water content is high, the ball will be sticking to the plates. um, if you want to understand this more, you can make try making chapatis at your home this week. Okay, it's similar to a wheat flour where you roll it with a little amount of water. You will see large amount of cracks. You add little by little water, you slowly roll it. At one point of time, you can see that it will make a perfect ball without sticking to your palm. And if you add more water, it will stick to your palm very well. It will stick, and you won't be able to make threads. Okay, so something like that. So when the water content is high, you will not be able to make the thread. So when the water content is closer to plastic limit only, you will be able to form the thread. You can slowly make the thread by on a glass plate using your palm. And you have to make sure that it's a 3 thread. So this 3 thread, when it will be crumbling at one point of time, it will be crumbling. So you have to take the crumbled pieces and you have to keep it for water content. Okay, so you have to take the crumbled pieces and keep it for water content, so that will give you the plastic limit. So you know what is liquid limit and we know what is plastic limit. Both are going to be water contents. Okay, so we are measuring the water content, and we can now classify the soil. Okay, so you know what is the liquid limit and plastic limit. This is a standard chart. So if the value you obtained is going to lie above this line, then it is going to be a clay soil. It can be of high compressibility or low compressibility. This is low compressibility and high compressibility. O is nothing but organic soil. So we'll when we are going to have organic content very high, then we have to classify the soil as organic soil. Um, so or else, if the point that you are getting is going to lie below this line, it can be of silt of low compressibility or silt of high compressibility. So anything above the line is going to be clay, anything below the line is going to be silt. Okay, so this we call it as plasticity chart, and this we call it as a line. The equation of this a line is very much important. 0.73 liquid limit minus 20 percentage. Liquid limit should be substituted in percentage. Okay, so this they have asked many times in competitive exams. There are equation for a line 0.73 ll minus 20. Okay, so the next one, the third one, is going to be your shrinkage limit. So for shrinkage limit, you can see you have standard shrinkage dishes. These we call it as shrinkage dishes. So what we have to do is we have to prepare the soil first. So you have to take the soil which is having more than your liquid limit water content. The soil should be in more than its liquid limit water content, and the soil has to be filled in 3 layers by tapping this shrinkage dish on a rubber pad. So you have to fill the soil of in this smaller cup. Like you have to take a small scoop of soil, fill it, tap it very well, so that air should be released from the voids if we present. Okay, so you have to fill it in 3 layers, and then you before that you have to apply grease. I just missed out. You have to apply grease to the inner surface of this dish, then fill the soil in 3 layers, tap it, and neatly flush out any excess soil, and keep it for air drying for 24 hours. And then you have to keep it in a oven. Straight away we cannot keep it in oven, because then it will have large amount of cracks. So again, as I said, it's going to be a water content, but we are not directly measuring the water content as we do in liquid limit or plastic limit. You have to know the empty weight of this cup, then fill the soil in 3 layers, measure the wet weight, keep it in air drying for 24 hours, then oven dry it, then find the dry weight. So you will have a water content. So that is not exactly the shrinkage water content. We have to find out the volume of this dish. and the volume of the dry pad that is formed, then only we'll be getting what is the shrinkage limit water content. So take petri dishes and you have to apply a coat of grease. So mix the soil with more water than its liquid limit. That's why they said slightly flowing, and put it in the petri dish, tap it, and place it on the oven for above oven for 24 hours, and then you place it inside the oven and find out what is the dry weight. Okay, so here you have a petri dish. We have filled it with three layers of the soil. Measure the weight, then oven dry it and measure the weight. Now you will find the soil in somewhat in this way. You can see that there is an annular gap formed. Okay, the soil has shrunken and it has come to the center here. Okay, the soil has shrunken and come to its center here. So this is the oven dried soil. What we have to do is, you are going to find out what is the volume of this dry pad and volume of the cup, which is equal to the wet pad. Okay, so how do I find the volume of this cup? You have to fill the mercury in this cup, and you have to use a glass plate, press it so that it is leveled, and measure what is the weight of the mercury inside the cup. So that weight will give you, that weight divided by unit weight of mercury, that is 13.6, will give you volume of the cup. So this volume of the cup is equal to the volume of the wet soil. Okay, then you have to find out what is the volume of this shrunken soil. So what we have to do is we take a separate beaker kind of thing, separate beaker, and we fill it with excess mercury, level it, and then after leveling, you place the soil pat on the top of mercury and press it with the glass plate with the prong. It will have small needle kind of thing in the glass plate. You press it well, so that you press it well, and the pad will be immersed inside well, and mercury will be flowing out. Okay, so you measure what is the mercury that is that has come out. Okay, because of immersion of your dry pad, there is excess mercury flowed out. So you measure what is the weight of this mercury. So this weight divided by volume will give you the volume of the dry pad. Okay, so we measure what is the volume of the dry pad, volume of the dry soil pad. Now your shrinkage limit is nothing but, from this formula you can see that m2 is weight of dish plus wet soil minus m3, that is weight of dry soil plus uh, your dish weight, minus v1 minus v2. V1 is nothing but volume of wet pad, v2 is nothing but volume of dry pad. You can see volume of dish, that is volume of wet pad, minus volume of dry pad, into gamma w, which is going to be 1, divided by m3 minus m1. M3 minus m1 is your dry soil weight, that is weight of dry soil plus pad minus your weight of empty dish. Okay, so from this formula we can find out what is the shrinkage limit water content of the soil. Okay, so that means that this, at this water content, even if you decrease the water below this water content, the soil will not undergo any volume change, that is it has shrunk to this some constant level. Okay, beyond this, the soil is not going to decrease in its volume. There is a shrinkage limit water content. Okay, so do anyone have doubt till this? I'll just stop the presentation. For till now we have discussed about calibration of hydrometer, then we have discussed about liquid limit, plastic limit, and shrinkage limit. Does anyone have doubt in finding of any of these parameter? So there is no doubt. So you have, please. Pardon? No, I'm not able to understand. Solay Raj, can you be more clear, or you can put it in the chat box? Okay, no doubts. Okay, thank you. Thank you for your response. Fine. Anyone else? If you have any doubt, you can even put it in the chat box. If you are, if you don't want to turn on your mics or anything. So we are clear with liquid limit, plastic limit, and shrinkage limit. So all these three limits are nothing but water contents of a fine grained soil, which will help you to understand the behavior of soil, and also which will help you to classify the soil. That is the main purpose. That is a very prime most important classification of soil. So generally only if we classify the soil, we'll be able to know its other behavior. For example, if you have going to have a clay of high compressibility, if you are going to classify the soil as clay of high compressibility, then it indicates that your clay will swell lot, it will shrink lot, it will going to cause a huge volume expansion. It can cause severe settlement. Okay, the consolidation of ch clay will be very high, so it will cause huge settlement and consolidation. So all these things we can get just by classifying the soil. Yeah, yes, Madhu, do you have any doubt? Okay, we'll move on to the next thing, that is going to be compaction. Okay, so compaction is very much important when you are going to use our soil for any construction purposes. Okay, and also if the natural soil, if the natural soil, like even in case of sand, okay, if it is going to be existing in a very loose state, so compaction is the process which will help you to increase the densify the soil. Okay, when we go for any construction purposes in Dubai and Arab countries, you can see that the sandy soil in that in those area will be of very loose condition near to the surface. So they will be using vibro compaction. They will be using other methods like lift and drop method to compact the soil. Okay, so in that manner, for sandy soil, compaction will be done. But when it comes to clay soil or C5 soil, clay mixed with sand, C5 soil, whenever we are going to construct it for pavements, for runways, for soil nailing wall, for filling of our flyover retaining walls, in retaining walls, etc. Wherever you are, when you are going to fill the soil and use it, we have to compact the soil so that it will get a denser configuration. So compaction is nothing but reduction of voids by applying energy. Okay, so we are in the compaction, there are two important parameters. One is going to be I'll just write it. Okay, one is going to be gamma d max. So what is that? We are going to find out. Okay, when we go talk with highway people or anybody, they will be always concerned with these two parameters, that is a maximum dry density and the optimum moisture content. Maximum dry density and optimum moisture content, these are the two things that we are going to get as a result from our compaction test. Okay, so Proctor is a scientist who has developed this principle. So we know that from our even in the past, there used to be builders have recognized the importance of compacting the soil so that it is going to produce a strong, settlement free, and water resistant mass. So by compacting, what we are going to create, we are going to create a denser mass, denser configuration, and it is going to have good strength, and also it is going to give you very less permeability. So the permeability through the compacted soil is going to be very less, and also it is going to have a very less settlement, so it is not going to settle lot, so it is going to have a very less settlement. So the densification of voids, that is what very much important. So when you compact, so any process in soil, whether it's a compaction or consolidation, the change is subjected to the voids only, the solids will remain constant. We are not going to do any change, we are not going to reduce the size of the particles or anything. Whatever the change that we are going to do is going to reflect only in the voids. Okay, so that's why void ratio is very much important in soil. Void ratio, if you remember, is nothing but volume of voids to the volume of solids. Solids is always constant, volume of solids is always constant. Any change whether water is going to enter, water is going to expel, or particles are going to come closer, or anything is going to happen only to the voids. So the densification of voids is going to happen, which is going to increase the strength of the soil. So this pic will be able to help us to remember the process of compaction. So they are spreading the soil, and you are spraying water, sprinkling water, and we are the road rollers moving. So when we spread the soil, okay, I'm going to compact it, but I don't know at what water content or how much water I have to add. If I'm going to add excess water, that's all, it is going to cause stickiness. I'm going to not get many chapatis. Okay, so it is going to stick to the bottoms and everywhere. So water is very much important factor. So how much water I have to add. The second thing is, how do I know whether it is compacted or it is densified to its maximum? uh, that I have to know. And whether okay, I'm going to compact this layer. Okay, so you have to spread the soil in layers. So you'll be filling the soil in layers, and then you are compacting. Once this layer is compacted, then you put another layer, then this is compacted, then you put another layer, and this is compacted. So how much thickness of soil I have to put, or in how much thickness I have to run for very good compaction, whether it is going to be 5 centimeter or 10 centimeter or 15 centimeter, at which height of lift, we call that as lift thickness, it is going to get compacted. Then the third question, how much times I have to run this road roller to and fro, number of runs. Okay, so how much time it has to go to and fro to have a very good compaction. All these things is a question when we are going to use the natural soil for as a medium, or when we are going to spread it and compact it. So all these things we are will be able to get an answer only when we do a laboratory compaction test. So R.R. Proctor is a scientist who devised this test, which is possible to determine the moisture content that will give you the maximum density with the selected expenditure energy. Okay, so when we are going to apply energy, and we are going to find out the moisture content at which it is going to attain a maximum density. Fine. So what happens is, initially when you are going to add water to the soil, okay, the soil will absorb a film of the soil will absorb the water. So this is your soil particle, and this is going to be another soil particle. Okay, so when you are going to add water, okay, this water will be absorbed to the surface like this. Okay, so it will be absorbed like this, and when I compact it, so these two particles will come closer, and this water molecule will act like a lubricating agent for the particles to roll over one another. So when I'm compacting, the particles can very well roll over one another, and they attain a denser configuration. Okay, so when they roll over one another, they get a find their specific position, and they get form a denser configuration. So this is the role of water. So it is going to act as a lubricant. That is a very important thing. Okay, so it is going to slide easily over one another, and it is going to help me in attaining a very good compaction. So because of this lubrication, the addition of small amount of water up to a certain amount, it will replace the air from the soil voids. So as you add water, we are going to replace, when you compact it, the voids are removed, and the water is replacing the air between the voids. But after very high water content, what happens? So at a higher water content, these water will occupy the space between the voids, and it will it will reduce the density of the soil mass. So initially when it is in lesser amount, it will be acting like a lubricating agent, but when the water content goes beyond a particular limit, okay, it will not help you with the forming a denser configuration. This you will feel when you do the compaction by yourself. If when you slowly add more and more water, you can see that the soil will be coming in the sides. when you compact with the rammer, there is a rammer. So when you compact it, so the soil will be coming to the sides. It shows that the water content is very large. Therefore, there is an optimum moisture content which will give you the maximum dry density. That is a maximum denser configuration which the soil can attain. Okay, not that water content is what we call it as optimum moisture content, OMC. We call it as OMC, and at that water content, if you compact, it will attain its maximum dry density. Okay, this graph is a very helpful. See, I have plotted the graph between dry density versus water content. Dry density versus water content. So initially, when you add, this is going to be at a lesser water content. When you add water, slowly when you increase water, the water will help for more and more lubrication. So the slowly the particles get sliding over one another, and at one point of water content, it will attain a maximum dry density. And after this point, okay, when you add water, what happens is the soil will have a the water molecules will occupy more space between the soil particles, and the density will decrease. Okay, so we call in terms of soil fabric, closer or this side we call it as dry, this side we call it as dry of optimum, and this side we call it as wet of optimum. Okay, so in dry side of optimum, the soil will be of going to be flocculated structure. We call this as flocculated structure. And when it comes to wet of optimum, it will have a dispersed structure. Dispersed means it will be like this. There will be particles will be oriented in this manner. When it is having flocculated structure, flocculated means like there will be contact between each particle, and they will have a very good denser density. Okay, so we call it as dry side and wet side. Okay, so you have to calculate what is the zero air void line. We call that as a zero air void line. That is when we are going to add a particular water content, and imagine if you are if you are removing the entire voids. I mean, for that water content, for that particular added water content, if you are able to remove the voids, and if you are finding the dry density, that is we call it as zero. From that we get dry density, from which we are plotting a zero air void line. See, the purpose of this zero air void line is in a graph. So we are plotting dry density versus water content. So you get a curve like this. So you'll get a zero air void line like this. This is corresponding to 100% saturation. So this gap will tell you how effectively you have compacted, or how effective is your result. If this gap is large, it means that your compaction, you have not done the compaction very well in the lab. So if this distance is as close as possible, then it has mean that the compaction is done very well. Okay, so this zero air void line will tell you that this is a density where for a corresponding water content, where your all the voids are replaced with water, but that is not practically possible. Okay, this is like a theoretical density, we can tell. Theoretically, for that water content, what could be the density attained if you are replacing all the air voids with water. So this is your practical density. So if your graph is as closer to this zero air void line, it is like your compaction is very good, fine. So these are the equipments. One is going to be the base plate, then we have a mold, then we have a collar or extension, then we have a rammer. Okay, rammer, this is a rammer. So this is a standard proctor. We have two types of compaction. The first one is standard proctor compaction. So you note down all the dimension of the collar, then mold, then the weight with the plate and the mold. Okay, so first measure all the dimensions, diameter and height of this mold, then measure what is the weight of this mold plus base plate, then apply oil to all the surfaces, then put the collar on the top. Then you have to take approximately 3 kg of soil, mix it with water. You have to start with some 4 or 6 percentage, mix it with water. Then you fill the soil in three layers. Okay, so you have 3 kgs means approximately you split the soil in three parts. Then you fill the soil in three layers. So each layer, fill the first layer with the rammer, you have to give 25 blows. Okay, you have to give 25 blows. You have to give it in a circular manner. Then first layer is filled, 25 blows is given. Then scratch that layer, because you have to give bonding to the first layer and the another layer. So scratch the layer, then fill the second layer. Okay, then again compact it, give 25 blows, then scratch it. Then again fill the third layer soil, compact it. Then it will be like a little bit higher in your collar. Then slowly remove this collar, remove the excess soil. Okay, so then measure the weight. So measure the weight of mold plus soil plus base plate. Okay, so this is the procedure. Then you eject the soil, break it. For general laboratory purpose, you break it and you again mix it with water, higher amount of water. Then you have to repeat the procedure. For research purpose, I just want to tell you that what we do is, we never use the same soil for the entire test. We will take around 5 packets of 3 kgs. For example, 5 packets of 3 kg soil. All the soil will be mixed with different water contents like 6, 8, 10, 12, 15, 18. Okay, depending on the soil, we'll be choosing the range of water content. So that range is actually also closer to your plastic limit. Your OMC, just to, this is given in IS code, your OMC will be closer to your plastic limit water content. So this, once you know that is plastic limit water content, you can get an idea what could be your OMC is. So if you are going to have plastic limit around 25 percentage, for example, then you take 5 packets of soil. 5 packets of, this is for research purpose, I am just telling you. Okay, so you mix this with 18 percentage water, this with 21 percentage water, this with 20 to 20, 25 percentage with water, this with 28 percentage, and this with 31 percentage. So different soil, all the soil will be mixed with different percentage of water. Then we do the same procedure. Okay, instead of using the same soil again and again. Okay, so this will give you more reliable results. And also we mix the water and we keep for 24 hours of hydration, uh, so that the water content is actually equally distributed. We don't mix the soil and do the test immediately. So we keep it for 24 hours of hydration, 24 hours for equilibration. And then we do the test. Okay, it is going to be the same procedure. Then fill it in three layers, compact each layer with 25 blows, and measure the weight. Okay, fine. Okay, so you get a, one second, yeah. So you note down what is the mold dimension, diameter, height, volume of the mold. Then you find out these are the other formula used. So you have to take water content from the mixture, I mean from your trials. So each trial, from each trial, you have to take water content. So you are breaking some for in this case, you are breaking the ejected soil. Your soil will be ejected. So you have your mold here, you have a ejector. Okay, so this is a hollow mold. Okay, so you'll be ejecting the soil and you'll be taking the soil, and you'll be breaking the soil into parts. So this parts, from this you take it for water content. So you find what is the water content for each trial, and you know what is the weight of compacted soil plus mold from each trial. This is what you are going to find out. Okay, so your water content will be increasing. And after sorry, your weights also will be increasing. So as you increase the water content, after a particular water content, after a particular level, the weight will decrease. Okay, that will show you the termination of the test. So you'll be plotting the graph between water content versus dry density. So dry density is nothing but weight by volume will give you the bulk density divided by one, your 1 plus w. here. Your bulk density divided by 1 plus water content will give you the dry density. So we'll be getting this graph from our calculations, and we'll be noting down what is the peak value. Okay, so that is going to be the maximum dry density, and this is going to be the optimum moisture content. So it means that if you are going to compact at this water content, you'll be able to get the maximum densest configuration of for that soil. Okay, and this is your zero air void line. Fine. So these are the dimensions of the Proctor hammer and the mold. Okay, you can just go through this. Fine. So modified Proctor compaction. So for this table, it is very much easy to remember, and it is very much important to remember. So when we go for um, runways, etc., where you are going to, where the weight is going to be huge, okay, so that time we cannot compact with a standard Proctor density, so we have to go for another type called as modified Proctor compaction. So what is the difference between modified Proctor compaction is, you can see this table. So in standard Proctor compaction, you are going to use 25 blows, modified also 25 blows. The number of layers, first and foremost difference is number of layers. So in modified, you will fill it in 5 layers, whereas in standard you will fill it in 3 layers. You are filling the soil now. So in standard you will be filling as a 3 layer, whereas in modified you will be filling it as a 5 layer. Same. And height of fall, so your rammer is going to be different for a standard and a modified. So this rammer, if you see, this is a standard Proctor rammer. The weight of this rammer is going to be around 2.5 kg, whereas for modified it is going to be 4.5 kg. I just want to give it as a rough number. Exact number is 2.6 and 4.89, but generally for remembering purpose we keep this as 2 as a number. Okay, so the weight of the rammer is going to be 2.6, and here it's going to be 4.89. Height of fall, you are lifting the rammer and you are leaving it. Okay, so it's at a free fall, it will fall. It's going to be 31 centimeter here, and it is going to be a 45 centimeter for a modified. So modified, it is going to be 5 layers, and the weight of rammer is going to be 4.89. Height of fall is going to be 45. That is the difference. Where in standard it is 3 layers, weight of rammer is 2.5 kg, and height of fall is 30 centimeter approximately. Okay, as a round of number. So when you go for a modified Proctor compaction, as you can see, the energy and the densification attained is going to be larger in the modified Proctor compaction. So this is a curve for a same soil. For a same soil, you can conduct a modified Proctor and a standard Proctor. If you see, the density will be, for a modified Proctor test, the density will be higher. You can see here it is going to be 2.05 or something, it is 2.2. So the density will be higher, and the water content, optimum moisture content, will be lesser when you are going to use a modified Proctor. Okay, so in modified Proctor, the attained density will be higher. So your gamma D will be higher, and your water content, optimum moisture content will be lesser when compared to the your standard Proctor test. Okay, so here we are using a higher energy. So but the mold and everything is going to be the same. Okay, there is no change in the size of the mold or anything. Only the rammer and the number of layers is going to differ. Okay, the energy, if you see, it is going to be 593 kilojoules in a standard, whereas here it is going to be 2698 kilojoules per meter cube. That is the energy coming. Okay, fine. So the next we'll discuss a little about permeability. Okay, so as I said, when you are going to compact the soil, its permeability, there are going to be three engineering factors, as I said: permeability, shear strength, and settlement. When you're going to compact the soil, permeability will decrease. shear strength will increase, settlement will decrease. Okay, so when you're going to have a compacted soil, the permeability will be very low. There will be lesser voids, lesser space for the water to flow through. So what is this permeability? It is measured in, anyone can tell the unit, permeability unit? Yes, can anyone tell the unit for permeability? Okay, it's in meter per second or centimeter per second. We measure it in meter per second or centimeter per second. So it is a property of the soil or a porous medium by virtue of which water can flow through it easily is called as permeability. The ease of water to flow through it. Okay, the ease of water to flow through it is called as permeability. So when the water can easily flow through, it called high permeable. When the water can flow at a very slower rate, we call that low permeability. It is a very important geotechnical parameter. In the lab, we find it using a constant head test and a falling head test. Two types of lab tests are there. Okay, so in general, gravel will have a high permeability when compared to sand, and the clay has the least permeability of all. Okay, so if you are going to pour water in a clay, it will take a large time to for the water to come through the exit. So we follow Darcy's law. That is a based on Darcy's law only, the formula for permeability is framed. So he experimentally demonstrated that for a laminar flow condition in a saturated soil, very important. Every word is important in this definition. In laminar flow condition in a saturated soil, the rate of flow per unit or discharge per unit time is proportional to its hydraulic gradient. See, whenever you are going to have uh, any flow where where like temperature or a current or anything is going to flow from one area to another area only if you are going to have a gradient. Okay, when there is no gradient, when there is no difference between two levels, then there is no flow going to happen. For example, if the temperature is going to be in the same in two rooms, there is no flow going to be happen. Whereas when you are going to have a cold room and when a hot room, and when you are opening the doors, so the temperature will be flowing from one area to another and you are attaining a equilibrium. Okay, so for water to flow through a soil, you have to have a hydraulic gradient. We call it as a hydraulic gradient, which is nothing but head loss to the length of flow. We call h by l. That is what we call it as hydraulic gradient, h by l, head loss to the length of flow. We'll discuss here. So your discharge q is proportional to uh, I into a. For that proportionality is removed by your factor called as k, which is the permeability. Q equal to kia. K is permeability, I is hydraulic gradient which has no unit, and a is the area of the total cross sectional area of flow. So you can see here you have a soil sample here, and you have a level of water at this point, and you have a level of water at this point. So once you open this, if you imagine if this is going to be a gate, once you open these two gates, the water will be flowing through the soil in this direction. Okay, till this level. So what is that causing this flow? This head difference, the head difference between these 2 points, we call that as head loss. So this head difference divided by the length of the sample, the length of the soil sample, that h by l is what we call it as hydraulic gradient. Okay, so h by l, that we call it as hydraulic gradient, which is going to cause the flow. So what could be the factors that is affecting the permeability of a soil? When it comes to permeability, there are many factors. One is, foremost is going to be a grain size, as I said, if whether it's a gravel soil or a clay soil on a general. Okay, so first and foremost is your grain size. Next, your property of the pore fluid. It is not always water is going to flow through, sometimes it can be even a chemical uh, contaminant flowing through the soil. Okay, so it depends on the pore fluid of your flowing material, then your void ratio of the soil, structural arrangement, as I said, it's a denser or looser manner, or whether it's a flocculated particle or a dispersed particles, then entrapped air inside it. Entrapped air means whether it was uh, when your soil is going to be fully saturated, all the air voids will be removed. Okay, so you have to make sure that it's fully saturated, or else the entrapped air can affect your permeability result. Absorbed water in the clays, the water that is absorbed to the surface of the clays. Okay, so numerous factors influence the permeability coefficient. Fine. Okay, I hope I have come to the final portion. So, how do we measure this permeability in lab? We have two methods. One is called as constant head method and falling head method. Okay, which method is suitable for which type of soil? So, your constant head method, that method is suitable for coarse grained soils. You remember CC. And your falling head method, it is suitable for fine grained soil. Why? Because is when we once we know why how these tests are conducted, then you will understand, okay, this is why this method of testing is suitable only for coarse grain. This is why once we discuss the how this test is conducted. For example, in constant head method, we will be collecting the discharge, we'll be collecting the water coming out of the sample. Okay, so that will be easy for us when we mean that we'll be able to collect the discharge when it is a coarse grain soil, whereas in a fine grain soil we will not be able to collect the discharge because it's a very slow permeation of water is happening, so the discharge will be coming in drops. Okay, so or sometimes very it takes longer time for the discharge to come out through the soil. So in that time we will be measuring a head drop, so you'll have a burette, you'll just note down how much water has how much water head has come down from one level to another. We cannot measure this head drop in a constant head method. Why? Because the flow will be faster, so the head drop will be very fast from one level to another. Okay, so I'll discuss that in detail when we go into further. So currently time being, your constant head method is suitable for coarse grain soil, and your falling head method is suitable only for fine grain soil. So there are other field methods like pumping out, pumping in, and indirect methods, as I said, from grain size. If you remember, I related K to some D value. F- Just recollect what is that D, whether it's a D10 or D50, D60 or D30. Okay, when you know that D value, particle diameter, then you will be able to find out what is the permeability. And horizontal capillarity test and consolidation test data, you can use that to find out the permeability. Okay, so with this, I am winding up. Is there any other doubts? Any doubts? We have seen about calibration, liquid limit, plastic limit, shrinkage limit, compaction. So in compaction, we have standard compaction and modified compaction, standard Proctor compaction and modified Proctor compaction. The difference between these two tests. Okay. So any doubts? Yes, sir. Okay, sir. Okay, sir. Okay. Yeah, reusing is fine, but we if you are, if we don't have an ample supply of soil, okay, we can reuse it. It's not but we have to make sure that we are breaking the ejected soil very well, and we have to ensure that the mixing is proper, and we have to mix the waters very well, and we have to mix it for research purpose, since we need much accuracy. I can say that we'll be using different weights of soil with different percentage mixed up, and also we'll be spray mixing. We'll have a spray that we use in saloons, and we'll spray mix the water so that the moisture content is equally distributed. But in general laboratory purpose and other way other play mean things. I've seen people mix, just pour the water and mixing it. Okay, so there will be some errors because of that, but it doesn't matter. When we don't have that ample supply of soil, it's okay to do with the same soil also. We can slowly increase the water and we can find out the density. Yes, sir. No, sir. There is that is not required. Any of the tests it doesn't need any temperature control. Whereas in hydrometer, we have to find out the temperature of the suspension at that particular time. The every time that like whenever we are noting down the reading, we should insert the thermometer in the suspension, and we have to find out the soil suspension reading. What is the temperature of that soil suspension at that particular time. So temperature effects are not there for a liquid limit or plastic limit or shrinkage limit, and even for compaction temperature is not going to affect much. Generally we go for 24 hours, sir. From starting from 30 seconds we'll be starting our reading. So 30, 1 minute, 2 minute, 4 minute, 8 minute, then 1 hour, 15 minutes, 30 minutes, 1 hour, 2 hour, 4 hour, 8 hour, 12 hour, then 24 hours. We conduct the test for 24 hours. No, doesn't matter like early morning, but we have to if you see the reading, you can start starts from 30 seconds. Okay, yeah. No, for example, if I'm starting at today morning 8 o'clock the test, so my 10-hour reading will be night 8 o'clock, my 24-hour reading will be the next day. So within that, if I'm able to get 12-hour reading is fine. 8 and 12-hour reading is fine. Then straight away it goes to 24 hours. Yes, sir. Yes, sir. There is a link provided in the Google spreadsheet. I don't know whether we have. I can show you. I am every week. I am pasting the link in this spreadsheet. Do you have access for the spreadsheet? This spreadsheet access will be provided to you in the NPTEL course thing. If you're able to access this spreadsheet, then you'll be able to access the presentation. Yeah, it is there, I believe. I have not checked it, but for previous courses I have checked it. So it was, this link was available. I'll just make sure whether this is, I'll just check it and let you know whether it is available. So through this link you can access the spreadsheet, and this spreadsheet will have the presentation folder link from where you can get your get this presentation. Yes, sir. Thank you, sir. Yes, any doubts? Okay, I hope this discussion will help you to solve the week 2 assignment. I have gone through the assignment and I have made the presentation closer, I mean, help you in such a manner to solve your assignment. Okay, so if you have any doubts or anything, please post it in the YouTube or discussion forum. Okay, thank you.